4 billion years ago, you could reach up and almost touch the moon. It hung in the sky 30 times larger than today, a monstrous disk dominating the heavens. Days were 18 hours long, not because time worked differently, because Earth spun faster. Tides rose hundreds of meters, scouring coastlines twice daily. The moon was so close, so massive in appearance, that it would drive you mad if you saw it. But here's what's strange. That alien Earth, with its huge moon, short days, and apocalyptic tides, is why you exist. The moon is escaping. Right now, drifting away at 3.8 centimeters per year, about the rate your fingernails grow, and as it leaves, it takes angular momentum with it, slowing Earth's rotation, making days longer. 4 billion years ago, a day was 6 hours. 2 billion years ago, 18 hours. 500 million years ago, 21 hours. Today, 24. In the future, longer still. The moon is dying, slowly. And when it's gone, if Earth lasts that long, our planet will wobble. Seasons will become chaotic. Climate will destabilize. The moon isn't just a pretty object in the sky, it's our stabilizer, our timekeeper, our shield. And it's leaving. Let's go back to when it was close and see what Earth was like when the moon dominated everything. If you're fascinated by deep planetary history and the forces that shaped our world, please consider subscribing. This kind of research and storytelling takes significant effort, and your support makes it possible. Thank you. Let's start at the beginning. 4.5 billion years ago. The solar system is young, a spinning disk of gas and dust orbiting a newborn star, our sun. The sun ignited maybe 50 million years earlier. Nuclear fusion, hydrogen fusing into helium, releasing energy, light, heat. And around it, in the protoplanetary disk, matter is clumping, colliding, building. Dust grains stick together, electrostatic forces. Then gravity takes over. Larger clumps attract smaller ones. Planetesimals form, kilometer-sized bodies. Then tens of kilometers, hundreds. They collide. Sometimes they shatter. Sometimes they merge. And over millions of years, planets emerge. Rocky ones close to the sun. Gas giants farther out. Earth is one of those rocky planets, coalescing in the inner solar system, about 150 million kilometers from the sun. The habitable zone. Not too hot, not too cold, just right for liquid water, eventually. But at 4.5 billion years ago, Earth is nothing like today. It's a ball of molten rock, magma ocean, surface temperature maybe 1500 to 2000 degrees Celsius. No crust, no oceans, no atmosphere. Well, there's an atmosphere, but it's not air, it's vaporized rock, silicate vapor, carbon dioxide, nitrogen, water vapor from the rock itself. Heavy, thick, opaque. The surface glows, red, orange, like lava, because it is lava, the entire surface. And Earth is spinning, fast, very fast. A day at this point is maybe 5 to 6 hours. The planet is rotating rapidly because angular momentum from all those collisions accumulated. Every impact adds spin. And there have been countless impacts. Earth is still growing, still accreting material. Planetesimals are still raining down, bombarding the surface. Each impact adds mass, adds energy, keeps the surface molten. This is a violent time. The late heavy bombardment is coming later, around 3.9 billion years ago. But even before that, the inner solar system is a shooting gallery. Objects crossing paths, colliding, and one of those collisions changes everything. There's another planet, a protoplanet. We call it Theia, named after the Titan from Greek mythology. mother of the moon goddess Selene. Theia is roughly the size of Mars, maybe 10% of Earth's mass. It formed in the same region of the solar system, maybe at one of Earth's Lagrange points, stable gravitational regions, L4 or L5. 60 degrees ahead or behind Earth in its orbit, Theia grew there, in gravitational equilibrium, for millions of years. But that equilibrium is unstable. Perturbations, gravitational nudges from other planets, Jupiter, Saturn, Venus. Over time, Theia's orbit shifts, destabilizes, and eventually it crosses paths with Earth. They're on a collision course. And around 4.5 billion years ago, maybe 4.48 billion based on recent dating, they collide. The impact is not head-on. That would shatter both bodies, obliterate them. Instead, it's a glancing blow, oblique. Theia comes in at about a 45-degree angle, traveling at 10 to 15 kilometers per second. Relative velocity. Imagine a Mars-sized planet hitting Earth at that speed. The energy release is incomprehensible, equivalent to billions of nuclear weapons detonating simultaneously. Trillions. The impact vaporizes Theia instantly. Gone. The entire planet, converted to plasma, superheated gas, and a chunk of Earth's mantle. The outer layers, vaporized too. The cores merge. Theia's iron core sinks into Earth's core. They become one, and the vaporized mantle material from both bodies explodes outward. Some of it escapes to space, lost, but most of it enters orbit around Earth, a debris disk made of molten rock, droplets, clumps, orbiting rapidly. And here's the remarkable thing. Recent simulations published in 2023 suggest that this debris disk doesn't take thousands or millions of years to coalesce into the moon. It happens fast. Hours, maybe days. The material is hot, molten. It's sticky. Collisions cause clumps to merge, not shatter, because the material is liquid. And within hours, maybe 100 hours, the moon forms. A single body, coalescing from the debris, born from Earth's flesh. The moon is initially very close. Estimates vary, but around 15,000 to 20,000 kilometers from Earth. Compare that to today. 384,000 kilometers. The moon starts at about 5 to 6% of its current distance. Imagine that. From Earth's surface, the moon would fill a huge portion of the sky, maybe 10 to 15 degrees across. Compared to today, the moon appears about half a degree. 1 degree is twice the width of your thumb at arm's length. So the early moon is 20 to 30 times larger in apparent size. It's monstrous, a massive disk dominating the sky. You couldn't miss it. And it's hot, glowing, red hot, because it just formed from molten material. The surface is a magma ocean, just like Earth. Both bodies are molten, radiating heat. The moon is tidally locked almost immediately. Same face always toward Earth. Because it's so close, tidal forces are enormous. They lock the moon's rotation to its orbital period within maybe 1,000 years. And the moon is orbiting Earth rapidly. Because it's so close. Orbital period may be a few hours. It whips around, fast. And the tides. Oh, the tides. Today, tides are caused by the moon's gravity. The moon pulls on Earth, more strongly on the near side than the far side, because gravity weakens with distance. This creates a tidal bulge. Water on the near side bulges toward the moon, and on the far side, water bulges away, because the far side is pulled less. So you get two bulges. As Earth rotates, these bulges move, creating high and low tides. Today, the range is typically a few meters, 10 meters in some places with funneling geography. But when the moon is 15,000 kilometers away, The tidal forces are colossal. They scale with the inverse cube of distance. So if the moon is 25 times closer, the tidal force is 25 cubed, over 15,000 times stronger. The tides are not meters, they're hundreds of meters, maybe 300, 500? The numbers are debated, but they're enormous, and they occur twice per day, which at this point is twice per 6 hours. Every 3 hours, a massive tide sweeps across the planet, scouring the surface, reshaping the crust, creating tidal heating, friction. The tides flex the crust, the mantle, generating heat, adding to the already molten conditions. Earth is a hellscape. Molten surface, vaporized rock atmosphere, giant glowing moon overhead, tides hundreds of meters high. It's unrecognizable. But why do we think moon formed this way? The giant impact hypothesis. It's the leading theory, and it's supported by multiple lines of evidence. First, the moon's composition. Apollo astronauts brought back rocks, hundreds of kilograms, and we've analyzed them extensively. The oxygen isotope ratios in moon rocks are identical to Earth rocks. Oxygen has 3 stable isotopes: O16, O17, O18. Different solar system bodies have different ratios. Mars rocks have different ratios. Meteorites from asteroids have different ratios. But moon rocks, same as Earth, identical. That means they formed from the same material. The moon is made from Earth, literally. Second, the moon has a very small iron core, about 20% of its radius, compared to Earth, 55%. Why? Because the moon formed from the mantles of Earth and Theia. The iron cores merged into Earth. The moon got mostly silicate, mantle material. That's why it's less dense. Third, the moon is depleted in volatile elements, things that evaporate easily: zinc, potassium, sodium, water. Why? Because the impact vaporized material. Volatiles escaped, blew away. The moon formed from what remained: refractory material, things that don't evaporate easily. This all fits the giant impact model perfectly. And there's angular momentum. Physics requires that angular momentum is conserved. The Earth-Moon system has a certain amount today, and in the past it had the same amount, assuming no external torques, which is mostly true. The Sun adds some, but negligible over short times. So where did that angular momentum come from? The impact. Theia hit Earth at an angle, transferred momentum, angular momentum, caused Earth to spin faster, caused the debris disk to rotate, and that angular momentum is still in the system today, shared between Earth's rotation and the Moon's orbit. As the Moon moves away, it takes angular momentum. Earth slows. The Moon speeds up in its orbit, moves farther. It's a continuous exchange, tidal friction, and it's been happening for 4.5 billion years. We can measure it today, precisely, and we'll talk about that. But first, let's talk about what happened next. After the Moon forms, both bodies are molten, but they cool, radiating heat into space. The Moon, being smaller, cools faster. Within 10 million years, the surface solidifies, forms a crust. The magma ocean crystallizes. Dense minerals sink, forming the mantle. Less dense minerals float, forming the crust. Anorthosite, a light-colored rock, rich in plagioclase feldspar. That's what the lunar highlands are made of, the bright areas you see on the Moon. And then volcanism. The interior is still hot, partially molten. Magma rises, breaks through the crust, floods low-lying basins, creates the Maria, the dark areas, basalt, volcanic rock. This happens over the next billion years. The last major mare-forming eruptions are around 3 billion years ago, maybe 2. After that, the moon is geologically dead. No more volcanism, no plate tectonics. It's a static, unchanging world, cratered, bombarded by meteorites, but internally cold, inactive. Earth takes longer to cool, larger, more heat to lose. But eventually, it does. The surface solidifies, forms a crust. But unlike the moon, Earth remains geologically active. Plate tectonics, volcanism, erosion. The surface is constantly recycled. The oldest rocks on Earth are about 4 billion years old. Everything older has been destroyed, subducted, melted, recycled. But we have tiny crystals, zircons. From Western Australia, dated to 4.4 billion years. These zircons formed in water. We know because of the oxygen isotopes inside them. They came from rocks that interacted with liquid water. That means, incredibly, Earth had liquid water by 4.4 billion years ago, just 100 million years after the moon forming impact. That's fast. How? We're not entirely sure. The surface should still be hot, molten. But maybe the impact stripped away the early thick atmosphere, allowed faster cooling. Maybe water was delivered by comets and asteroids, wet planetesimals, bombarding Earth, adding water. And maybe, just maybe, pockets of the surface cooled enough for water to condense. Liquid oceans, forming early. This is radical. But the zircons don't lie. They require water. So Earth had water, early. And that changes the timeline for everything. By 4 billion years ago, Earth has cooled significantly. There's a solid crust, mostly oceanic, basalt. No continents yet. Those come later. The atmosphere is thick, carbon dioxide, nitrogen, water vapor, methane, no oxygen, anoxic. The sun is dimmer, about 70 to 75% of its current luminosity. So Earth should be frozen. Snowball Earth. But it's not, because the thick carbon dioxide atmosphere creates a greenhouse effect, traps heat, keeps the surface warm enough for liquid water, and the oceans are global, covering most of the planet. Maybe some volcanic islands, hotspots, but no large land masses. And the moon is still close. Not as close as initially. It's been receding, but it's still much closer than today. Maybe 50,000 to 100,000 kilometers away. Still 5 to 10 times larger in the sky than today. Still creating massive tides. And the day is still short, maybe 10 to 12 hours. Earth is spinning fast, and life is about to begin. Around 3.9 to 3.8 billion years ago, something remarkable happens. Life. The first living organisms. We don't know exactly how. Abiogenesis. The origin of life from non-living matter. It's one of the biggest questions in science. But we know it happened, because by 3.5 billion years ago, we have fossils, stromatolites, layered structures built by microbial mats, cyanobacteria and other prokaryotes. And we have chemical evidence, carbon isotope ratios in ancient rocks, suggesting biological processes. So life existed. Simple life, single-celled. Bacteria and archaea. Prokaryotes. No nucleus, no complex organelles. Just simple cells, but alive, metabolizing, reproducing, evolving. And where did it start? Possibly in the oceans, hydrothermal vents, underwater volcanic springs, rich in chemicals, energy, organic molecules, or maybe tidal pools, shallow pools along coastlines, alternately wet and dry as tides come and go. And here's where the moon comes in. Recent research, Nobel Prize-winning work, suggests that tidal pools are ideal environments for abiogenesis. the wet-dry cycles. When the pool is wet, molecules are dilute. When it dries, they concentrate. And chemical reactions that build complex molecules, polymerization, happen more efficiently in concentrated solutions, building RNA, proteins, lipids, the components of life. And the moon's tides create these cycles, regularly, predictably, twice a day. The moon may have literally created the conditions for life by driving tides, by creating tidal pools, by concentrating organic molecules. It's speculative. We can't prove it, but it's plausible, and it's poetic. The moon, born from catastrophe, becomes the midwife of life. By 3.5 billion years ago, life is established. Stromatolites are common. We find them fossilized in rocks from Australia, South Africa, Canada. These ancient microbial reefs, they're still around today, in a few places. Shark Bay, Australia, the Bahamas, living fossils, unchanged for billions of years. And these stromatolites preserve something interesting. Growth patterns, layers. Each layer represents a day-night cycle, or a tidal cycle. The microbes grow during the day, photosynthesize, trap sediment, build a layer. At night, they stop, or grow less, another layer. Over time, these layers stack up, and we can count them in modern stromatolites, in ancient ones. And what we find is remarkable. In rocks from 2 billion years ago, stromatolites show more layers per year, significantly more, around 480 to 500 layers per year. Today, there are 365 days per year. In the past, there were more, because the days were shorter, and we can calculate. If the year is the same length, Earth's orbital period around the Sun hasn't changed significantly. But there are more days, then each day must be shorter, and the math works out. 2 billion years ago, a day was about 18 hours, not 24. Earth was spinning faster, and we know this from fossils, from stromatolites, growth rings, like tree rings, but daily and tidal. They preserve the ancient rhythm of Earth's rotation and the moon's orbit. Let's go to that time, 2 billion years ago, the Paleoproterozoic era. Earth is unrecognizable, but becoming more familiar. The moon is now around 280,000 to 300,000 kilometers away, closer than today, but much farther than the initial 15,000. It appears maybe 30% larger in the sky. Still impressive, still dominant, but not monstrous. And the day is 18 hours, shorter than today. So the sun rises and sets more frequently, 486 times per year instead of 365. Sunrise every 9 hours, sunset every 9 hours. Day, night, rapid. And the tides, still powerful, much stronger than today, maybe 50 to 100 meters, twice per 18-hour day. Every 9 hours, high tide. The coasts are violent, constantly reshaped by water, and the moon hangs in the sky, massive. Unmoving if you're at a location where it's overhead, or rising and setting if you're elsewhere. It's tidally locked. Same face always toward Earth. The far side never visible from Earth. Hidden. And it's geologically dead by now. No volcanism. Just a scarred, cratered surface. Grey. Lifeless. But beautiful. Reflecting sunlight. Dominating the night. The Earth itself is changing. Continents are forming. Real continents. Not just volcanic islands, but stable land masses. Cratons. Ancient continental cores, made of granite, less dense than oceanic basalt. They don't subduct, they float, and they grow. Through volcanism, through collisions, plate tectonics is active. Oceanic crust forms at mid-ocean ridges, spreads, subducts at trenches, melts. The melt rises, forms volcanoes, and over time, volcanic arcs become continental crust, add to the cratons, build land masses. By 2 billion years ago, there are supercontinents, Knorland, Columbia, also called Lunar. These are collections of cratons, fused together through collisions, mountain building, orogeny, creating ranges, highlands and lowlands, river systems, erosion. The land is still barren. No plants, no animals, just rock. But it's there, emerging from the oceans, permanent land, and the atmosphere is changing dramatically. This is the time of the Great Oxidation event, starting around 2.4 billion years ago. But building up before that, what happened? Cyanobacteria, photosynthetic bacteria. They appeared sometime before 2.5 billion years ago, maybe 3 billion. They're using sunlight, water, carbon dioxide, and they're producing sugar and oxygen, photosynthesis. The oxygen is a waste product, toxic to many anaerobic organisms, but it's released into the water, into the atmosphere. At first, the oxygen reacts with dissolved iron in the oceans. Iron is abundant from hydrothermal vents, from weathering, and oxygen reacts with iron, forms iron oxide, rust, and it precipitates. Sinks to the seafloor, creates layers, banded iron formations, BIFs, alternating layers of iron oxide and silica, red and black. We find these all over the world, in rocks from 2.5 to 2 billion years ago. They're evidence of the oxygenation. The oceans are rusting, clearing, from murky red to clear blue-green. And eventually, once the dissolved iron is used up, oxygen starts accumulating in the atmosphere. It rises from trace amounts, less than 0.1%, to maybe 1 to 2%, still far below modern 21%, but significant. And it changes everything. Oxygen is reactive, corrosive. It reacts with methane. Methane was a greenhouse gas, keeping Earth warm. Oxygen destroys it, and the greenhouse effect weakens. Temperatures drop, and around 2.3 billion years ago, Earth experiences its first major glaciation, the Huronian Glaciation, possibly a snowball Earth event, ice covering most or all of the planet, lasting tens of millions of years. But eventually, volcanic CO2 accumulates, breaks the ice, melts the snowball, and Earth recovers. But the atmosphere now has oxygen, and that opens new possibilities. Aerobic respiration, using oxygen to metabolize, much more efficient than anaerobic, more energy per molecule. This will later enable complex life, eukaryotes, multicellularity, animals. But that's far in the future. At 2 billion years ago, life is still simple. Prokaryotes, bacteria and archaea, stromatolites, microbial mats, floating in the oceans, coating rocks, no land life. The continents are sterile, bare rock. But the stage is set, and the moon is watching, receding. Every year it moves farther, imperceptibly slowly, but cumulative. Over millions of years, the change is measurable. And as it moves away, tidal forces weaken. The tides get smaller, the day lengthens, Earth's rotation slows. Angular momentum transfers to the moon. It's a dance, a slow gravitational waltz, driven by tidal friction. Energy dissipates, heat, in the oceans, in the solid Earth. And that energy loss slows the rotation, pushes the moon away. It's inevitable, physics. And it will continue for billions of years until the system reaches equilibrium or until the sun dies, whichever comes first. Let's think about what living on 18-hour Earth would actually feel like. Imagine you're standing on a rocky shore, 2 billion years ago, the Paleoproterozoic. The sky is hazy. The atmosphere is thick with carbon dioxide and water vapor. But there's oxygen now, maybe 1 or 2%. You couldn't breathe it. Not enough. You'd suffocate. But it's there, changing the chemistry of everything. The sun rises. Fast. Faster than you're used to. It arcs across the sky, from horizon to horizon in 9 hours. 9 hours of daylight, then sunset, and 9 hours of darkness. The rhythm is relentless. Day, night, day, night. Twice as frequently as you're accustomed to. Your circadian rhythm would be chaos. Humans evolved for 24-hour cycles. Our internal clocks are tuned to that. On 18-hour Earth, you'd never adjust. You'd be perpetually jet-lagged, sleep-deprived, disoriented. But the organisms living then, they're adapted. Their metabolisms tuned to 18 hours. Their biological clocks synchronized to the rapid day-night cycle. It's normal for them. And the moon. Look up. It's huge. 30% larger than today's moon. Maybe more depending on where it is in its orbit. The orbit is slightly elliptical, so the moon's distance varies. Perigee and apogee. When it's closest, it looms, dominates, covers a significant portion of the sky. You can see surface features with your naked eye. The Maria, dark patches, basalt plains. The highlands, bright, cratered. The Terminator, the line between light and dark. Shadows of crater rims. Mountains. If you had a telescope, you'd see incredible detail. Craters within craters. Rays of ejecta. But you don't. You're a microbe. Or you're imagining. Either way, the moon is ever present, unmoving if you're on the equator where it hovers near the zenith, or rising and setting if you're at higher latitudes. And at night, it reflects sunlight. Earthshine also illuminates the moon's dark side. Earth is close, bright, reflecting sunlight onto the moon. So even the dark side of the moon has a glow. Subtle, blue. The whole system is brighter, more reflective, more interconnected. The tides are the most dramatic difference. Every 9 hours, the ocean rises and falls. Not a few meters, 50 meters, maybe more. The entire coastline floods, then drains, then floods again. If you're a stromatolite, a microbial mat clinging to a rock in the intertidal zone. Your life is defined by this rhythm. Submerged, exposed, submerged, exposed. When you're underwater, you photosynthesize. If you're cyanobacteria, harvesting sunlight, splitting water, releasing oxygen, building sugars. When you're exposed, you dry out, partially, concentrate. The water evaporates, leaves behind minerals, salts, nutrients. And when the tide returns, those nutrients dissolve, concentrated, available. This wet-dry cycle is powerful. It drives chemical reactions, enhances polymerization, builds complex molecules, RNA, proteins. It may have been essential for the origin of life, and now it's shaping ecosystems, microbial ecosystems. Simple, but thriving. And the tidal range isn't just vertical, it's horizontal. The tides move. As Earth rotates, the tidal bulge tries to stay aligned with the moon, but Earth is rotating beneath it, so the bulge moves, creates currents, tidal currents, powerful, sweeping across the seafloor, reshaping sediments, mixing nutrients, distributing heat. The oceans are dynamic, constantly stirred, and the energy comes from the moon, gravitational energy, and from Earth's rotation, kinetic energy, both being dissipated as heat through friction between water and rock, between water and water, turbulence. And that energy dissipation is what slows Earth's rotation. It's tidal friction, the mechanism behind everything, the moon's recession, the lengthening day. It's all connected, and it's measurable. Today, we can measure the moon's distance with incredible precision, laser ranging. During the Apollo missions, astronauts placed retroreflectors on the moon's surface, corner cube mirrors. When you shine a laser at them, the light bounces straight back. Scientists on Earth fire lasers at these reflectors. The light travels to the moon, bounces back, returns to Earth. The round trip takes about 2.5 seconds. The moon is far, and by measuring the travel time precisely, you can calculate the distance, down to the millimeter. And over decades of measurements, we've detected the moon's recession, 3.8 centimeters per year. That's the current rate, about 1.5 inches, the rate your fingernails grow, slow, but cumulative. Over 1 billion years, that's 38,000 kilometers. Over 4 billion years, the moon has moved from 15,000 kilometers to 384,000. That's a huge change, and it's ongoing. The recession rate isn't constant. It depends on tidal dissipation, which depends on ocean basin geometry, the shape of the continents, the depth of the oceans, resonances. Certain configurations enhance tidal dissipation, others reduce it. Right now, the North Atlantic has a near-resonant tidal period. The natural sloshing period of the basin is close to the tidal forcing period, so tidal amplitudes are large. Dissipation is high. The moon recedes faster. In the past, when continents were in different positions, resonances were different. Dissipation varied, so the recession rate varied. Sometimes faster, sometimes slower. But on average, it's been continuous, relentless. The moon is leaving, and there's nothing we can do about it. It's physics. And as the moon recedes, Earth's rotation slows. The two are linked. Angular momentum conservation. The total angular momentum of the Earth-Moon system is constant, ignoring external torques from the Sun and other planets, which are small. So if the Moon gains angular momentum by moving to a higher orbit, Earth must lose angular momentum by rotating slower. It's a zero-sum game, and we can measure Earth's slowing rotation. Atomic clocks, extremely precise, and historical records. Ancient eclipse observations. Babylonian astronomers recorded eclipses thousands of years ago, and we can calculate where those eclipses should have been visible if Earth's rotation were constant. But the observations don't match. They're off by hours because Earth's rotation has slowed since then. Not by much, but measurably. And we can use that to calculate the historical recession rate. And it matches. The physics checks out. The moon is receding. Earth is slowing. And it's been happening for billions of years. There's another way to measure ancient day length. Fossil corals. Corals grow layer by layer, daily and seasonally. Each day, the coral polyp secretes a thin layer of calcium carbonate, building its skeleton. And you can see these layers under a microscope. Daily growth bands, like tree rings, but daily. And if you count the bands between seasonal markers, summer and winter growth differ, you can count the number of days per year in the past. And paleontologists have done this with fossil corals from the Devonian, about 400 million years ago. And the corals show about 400 to 410 days per year. Today, 365. So Devonian days were shorter, about 21 to 22 hours, not 24. The math works, and it's consistent with the moon's recession. 400 million years ago, the moon was closer. Tides were stronger. Days were shorter. Everything fits. It's beautiful. Convergent evidence. From physics, from astronomy, from geology, from paleontology. All telling the same story. The moon is escaping. Now let's talk about what that means for Earth. The moon does more than create tides. It stabilizes Earth's rotation. Specifically, it stabilizes Earth's axial tilt. Obliquity. Earth's axis is tilted relative to its orbital plane, 23.5 degrees. That tilt is why we have seasons. When the northern hemisphere is tilted toward the sun, it's summer there. Winter in the southern hemisphere. 6 months later, it reverses. The tilt is constant, over human timescales. But over geological time, it varies, slightly, between about 22 and 24.5 degrees, over a 41,000-year cycle, Milankovitch cycles. These variations affect climate, ice ages, interglacials, but the variations are small, manageable. Life adapts. And the reason the variations are small is the moon. The moon's gravity acts on Earth's equatorial bulge. Earth is not a perfect sphere. It bulges at the equator because of rotation, centrifugal force. The bulge is about 21 kilometers. The equatorial diameter is 42 kilometers larger than the polar diameter. And the moon's gravity pulls on that bulge, creates a torque. That torque stabilizes the tilt, prevents it from wandering too much. Without the moon, the tilt would be unstable, chaotic, varying wildly, from 0 to 85 degrees, over millions of years. We know this because we can simulate it. Computer models, remove the moon, run the simulation, and watch what happens. Earth's obliquity starts oscillating, wildly, chaotically. Within a few million years, it's swinging from near zero, axis perpendicular to orbit, no seasons, to over 60 degrees, axis nearly parallel to orbit, extreme seasons. At 0 degrees obliquity, the equator gets constant sun. The poles get almost none. Permanent ice caps, frozen tropics in winter, boiling equator in summer. At 85 degrees, the poles point nearly at the sun. During summer, the pole is in constant daylight, for months, baking. During winter, constant darkness, freezing. The equator becomes temperate, mild. It's reversed. And these swings happen over geological time, mega years. But that's fast enough to disrupt climate, ecosystems, evolution. Complex life requires stability, predictability. You can't adapt to chaos, not easily. And without the moon, Earth would be chaotic, uninhabitable, or at least much less hospitable. Mars is the cautionary tale. Mars has 2 small moons, Phobos and Deimos, tiny, captured asteroids. They don't stabilize Mars. And Mars's obliquity varies, a lot. Currently, it's 25 degrees, similar to Earth. But over millions of years, it swings from 15 to 35 degrees, maybe more in the past, 45 degrees, 60. We see evidence in the Martian surface, layered polar deposits, ice ages, chaotic climate history. And Mars is cold, thin atmosphere, no magnetic field. Solar wind strips the atmosphere away. But the obliquity chaos doesn't help. It makes climate unpredictable, unstable. And Mars is dead, geologically. No plate tectonics, no volcanism, no life. At least none we've found. It's a frozen desert. And part of the reason is lack of stabilization. No large moon, no steady climate, no chance for complex life. Venus is another example. Venus has no moon. And it's strange. Venus rotates backwards, retrograde, clockwise as viewed from above the solar system. Every other planet rotates counterclockwise, except Venus. and it rotates slowly, very slowly. One Venus day is 243 Earth days, longer than a Venus year, 225 Earth days. So a day is longer than a year on Venus. Why? We don't know for sure. Maybe a giant impact early in its history flipped its rotation, or maybe tidal locking to the sun. The sun's gravity is strong. Venus is close. Tidal forces are significant. Over billions of years, they might have slowed Venus's rotation. Locked it, or nearly. And without a moon, there's no stabilization, no counteracting torque. Venus's obliquity is only 2.6 degrees. Tiny. Almost no tilt. Almost no seasons. But that's because it's nearly tidally locked to the sun, not because it's stable. If you perturbed it, it would wander. And Venus is hell. Surface temperature 470 degrees Celsius. Hot enough to melt lead. Atmospheric pressure 90 times Earth's. Thick carbon dioxide atmosphere. Runaway greenhouse effect. Sulfuric acid clouds. No water, no life. Venus is a warning. What happens when a planet doesn't have a moon? When tidal forces dominate? When climate goes out of control? It's not pretty. Earth is lucky. We have the moon. And the moon is the right size, the right distance. If the moon was smaller, it wouldn't stabilize the tilt. If it were much larger, tidal forces would be too strong. Earth might be tidally locked. One face always toward the moon. That would be bad. One side in perpetual daylight, heating. The other side in perpetual darkness, freezing. Extreme temperature gradients, brutal winds, uninhabitable. But the moon is just right. Goldilocks. Large enough to stabilize, far enough to avoid locking. And because of that, Earth has stable climate, predictable seasons, conditions suitable for life, complex life, us. The moon made us possible, not just by being there, but by being exactly the right moon, in the right place, at the right time. It's remarkable. And it's temporary, because the moon is leaving. In the future, as it recedes farther, its stabilizing influence will weaken. The obliquity variations will increase, slowly, over hundreds of millions of years. Eventually, billions of years from now, the moon will be so far that it barely affects Earth's tilt. And the tilt will start to wander, not immediately, but over geological time. And Earth's climate will destabilize. Seasons will become unpredictable. Ice ages will be random. Mega droughts, floods, chaos. Complex ecosystems will struggle, maybe collapse. Life will persist, probably. Microbes are resilient, but complex life, multicellular organisms, animals, plants, fungi, they need stability. And without the moon, that stability is gone. Earth becomes Mars, or Venus, or something else, something hostile. And if humanity still exists, we'll have to adapt, or leave, find another planet, with its own moon, its own stability, or engineer solutions, artificial stabilization, massive gyroscopes, who knows? But the point is, the moon is essential, and it's not eternal. How long do we have? Let's do the math. Currently, the moon recedes at 3.8 centimeters per year. At that rate, in 1 billion years, it will be 38,000 kilometers farther, from 384,000 to 422,000. That's about 10% farther. The tidal forces will be about 27% weaker. Inverse cube law. The stabilizing torque will be weaker too, but still significant. Earth's obliquity will still be relatively stable, but the variations will increase, maybe from 2 degrees to 3 degrees. Noticeable, but not catastrophic. In 2 billion years, the moon will be 60% farther. Tides will be much weaker, maybe a third of today's. The stabilizing torque will be weak. Obliquity variations will be several degrees. Climate will be less stable, but still manageable for life, for a while. But here's the thing. The sun is also changing. The sun is getting brighter as it ages. Fusion in the core converts hydrogen to helium. Helium is denser. The core contracts, heats up, fusion rate increases, luminosity increases. The sun brightens by about 10% every billion years. In 1 billion years, the sun will be 10% brighter. Earth will be hotter. The oceans will start to evaporate. Water vapor is a greenhouse gas, so more evaporation means more warming. Runaway effect. In about 1 billion years, maybe 1.5, Earth will become uninhabitable. For complex life, the oceans will boil off, the atmosphere will thicken, greenhouse effect will spiral out of control. Earth becomes Venus, and all of this happens before the moon's recession becomes critical. So in a sense, the moon's departure doesn't matter for Earth's long-term habitability, because the sun will kill us first. But on intermediate timescales, hundreds of millions of years, the moon's influence is crucial. And we're living in the golden age, when the moon is close enough to stabilize, far enough to allow calm conditions, and the climate is perfect for us. Let's go back to the 18-hour Earth, 2 billion years ago, and think about the biology. Life at that time is simple, but it's evolving. Prokaryotes are diversifying, different metabolisms, photosynthesis, chemosynthesis, aerobic respiration, anaerobic, fermentation, nitrogen fixation, sulfur reduction. Life is exploring chemical space, finding niches, adapting, and the environment is shaping life. The rapid day-night cycle, the extreme tides, the increasing oxygen, all of these are selective pressures. Organisms that can handle the 18-hour rhythm thrive. Those that can't, die. And over millions of years, adaptations accumulate. Circadian clocks, internal timekeepers, synchronized to the 18-hour day, genes that turn on and off, rhythmically, metabolic pathways that anticipate dawn and dusk, high tide, low tide. These rhythms are ancient, deeply embedded in all life. Even today, our 24-hour circadian rhythms, they evolved from shorter rhythms, from ancestors living on 18-hour Earth, and before that, 12-hour Earth, and before that, 6-hour Earth. The clock has been ticking since the beginning, and it's been slowing, gradually, and life has been adapting, gradually, tracking the moon's recession, tracking Earth's slowing rotation, evolution in real time, driven by astronomy. And here's something remarkable. The 18-hour day would have affected evolution directly. Metabolic rates, energy budgets. On a shorter day, organisms experience more frequent temperature swings, more day-night cycles per year, more opportunities for growth, for reproduction, potentially faster generation times, faster evolution, and the extreme tides. They create environmental gradients, from deep ocean to intertidal to terrestrial. Well, not terrestrial yet. There's no land life, but the gradient is there, submerged, exposed, wet, dry, and organisms living in those gradients experience strong selection, adapt, diversify. The tidal zone is a crucible for evolution, and the moon creates it. The moon drives the tides. The tides drive selection. Selection drives adaptation, and adaptation creates diversity. The moon is an engine of evolution, not directly, but indirectly, through its gravitational influence. On Earth, on the oceans, on life. It's all connected. Around 2 billion years ago, something extraordinary happens. Eukaryotes evolve. Cells with nuclei, membrane-bound organelles, mitochondria, chloroplasts in some, complex internal structure. This is a quantum leap. In complexity, prokaryotes are small, simple, limited. Eukaryotes are larger, more complex, more capable. They can grow bigger, differentiate, eventually become multicellular. But that's later. At 2 billion years ago, eukaryotes are single-celled. Protists, algae, amoebae. But they're the ancestors of all complex life, plants, animals, fungi, all eukaryotes, descended from these pioneers. And how did eukaryotes evolve? Endosymbiosis, one cell engulfing another, forming a partnership. Mitochondria were once free-living bacteria, probably related to modern alpha proteobacteria, capable of aerobic respiration, using oxygen. A eukaryotic ancestor engulfed one, didn't digest it, kept it. As a symbiont, the bacterium provided energy, ATP, efficient metabolism. The host provided protection. Nutrients, a stable environment. Over time, the two became one, inseparable. Mitochondria are now organelles, part of the cell, but they retain their own DNA, their own ribosomes, evidence of their bacterial origin, and chloroplasts in plants and algae. Same story. Cyanobacteria engulfed, retained, became organelles, photosynthesizers, turning sunlight into sugar, into energy. It's one of the most important events in the history of life. And it happened around 2 billion years ago, on 18-hour Earth, with the giant moon overhead. Did the moon play a role? Indirectly, maybe. The tidal pools, the wet-dry cycles, the oxygen, all moon-influenced. Oxygen enabled aerobic respiration, made mitochondria advantageous. Without oxygen, endosymbiosis might not have happened, or would have been different, less beneficial. So the great oxidation event, driven by cyanobacteria, photosynthesizing, releasing oxygen, that's the direct cause. But the cyanobacteria thrived in part because of environmental conditions, shallow seas, tidal zones, nutrient mixing, all influenced by the moon. It's indirect, tenuous, but plausible. The moon's influence reaches into the very cells of every complex organism, including you, your mitochondria, descended from bacteria that lived on 18-hour Earth under a giant moon. It's deep time, deep ancestry, and it's awe-inspiring. Now fast forward, 1 billion years ago. The day is maybe 20 hours. The moon is farther, but still closer than today. Life has advanced. Eukaryotes are diversifying. Some are multicellular, algae, seaweeds, simple animals, maybe. The fossil record is sparse, but there's evidence. By 800 million years ago, we have clear multicellular fossils. And by 600 million, the Ediacaran biota. Strange, soft-bodied organisms, fronds, discs, quilted structures. Not quite plants, not quite animals. Something else. Experimental. And then, 540 million years ago, the Cambrian explosion. Suddenly, the fossil record is full of animals, with shells, skeletons, hard parts, trilobites, brachiopods, mollusks, echinoderms, arthropods, chordates, the ancestors of vertebrates, of us. Diversity explodes. In 10 million years, the blink of an eye, geologically. Why? Oxygen levels rising, predation, arms race, ecological niches opening, and the moon. Still there, still stabilizing, still driving tides, creating environments. By 540 million years ago, the day is about 21 hours. The moon is closer than today, maybe 330,000 kilometers. Tides are stronger and life is thriving. On land, in the sea, everywhere. And then the colonization of land begins. Plants, around 470 million years ago. Early vascular plants. Simple. No leaves, just stems, but photosynthesizing. On land, creating soil, stabilizing surfaces, and animals follow. Arthropods first, millipedes, 450 million years ago, then arachnids, scorpions, and eventually vertebrates, tetrapods, amphibians, 370 million years ago. The story we told before. Tiktaalik, fish dragging themselves onto land. And the moon is part of that. The tidal zones, the intertidal environments, gradients from water to land, fish trapped in tidal pools, adapting, evolving, lungs, limbs, terrestrial capability. The moon creates the conditions, life exploits them, and the land is conquered by descendants of fish who owe their transition, in part, to the moon. By 300 million years ago, the Carboniferous Earth is covered in forests, massive forests, scale trees, giant ferns, horsetails 10 meters tall. Oxygen levels spike to 30%. Insects grow huge. Dragonflies with 70-centimeter wingspans. Millipedes 2 meters long. Amphibians diversify. And the first reptiles appear. Amniotes, with eggs that can survive on land. No need to return to water to breed. Full terrestrialization. And the day? About 22.5 hours. The moon continues its recession, 350,000 kilometers away now. Still closer than today, still exerting influence. The tides are noticeable, stronger than modern, but not extreme. Life has adapted. The forests depend on seasonal flooding. River systems shaped by tides, estuaries, deltas, rich ecosystems. The moon continues to stabilize Earth's tilt. Climate remains predictable. Seasons come and go. Ice ages cycle. Milankovitch rhythms. But within manageable bounds, life flourishes. 250 million years ago. The Permian-Triassic boundary. The Great Dying. The worst mass extinction in Earth's history. 90% of marine species gone. 70% of terrestrial vertebrates. The causes are debated. Massive volcanism, the Siberian traps, flood basalts covering millions of square kilometers, releasing carbon dioxide, sulfur dioxide, triggering global warming, ocean acidification, anoxia, a cascade of disasters, and maybe an asteroid impact. Evidence is controversial, but whatever the cause, life nearly ends. But it doesn't. It survives, recovers, and diversifies again. Dinosaurs evolve, mammals evolve, birds evolve. The Mesozoic begins, the age of reptiles, and through it all the moon is there, receding, slowly, stabilizing Earth, keeping the climate within bounds, even during catastrophes, even during mass extinctions. The moon is the anchor, the steady presence. That allows recovery. That allows life to persist. 100 million years ago, the Cretaceous, dinosaurs at their peak, T-Rex, Triceratops, sauropods, flowering plants spreading, angiosperms, bees, pollination, co-evolution. And the day, 23 hours, almost modern. The moon is 370,000 kilometers away, close to today's distance. The tides are nearly modern. The moon appears almost as it does now, in the sky. And 66 million years ago, another catastrophe. Chicxulub, the asteroid. 10 kilometers wide, hits the Yucatan Peninsula, releases energy equivalent to billions of nuclear weapons. Dust, ash, blocks the sun, impact winter, photosynthesis stops, food chains collapse, 75% of species extinct, including all non-avian dinosaurs. But mammals survive. Small, nocturnal, adaptable, and they radiate. diversify, fill the niches left by dinosaurs, primates evolve, hominids, Homo sapiens, us, and the moon. Still there, still receding, still stabilizing, making it all possible. Today, the day is 24 hours. The moon is 384,000 kilometers away. It appears half a degree across. Small, gentle, romantic. We barely notice it, most of the time. But it's still there, still pulling, still creating tides, still stabilizing Earth's tilt, still keeping climate predictable, seasons regular, and it's still receding. 3.8 centimeters per year. We've measured it, precisely, with lasers, bouncing off retroreflectors placed by Apollo astronauts. 50 years ago, humans walked on the moon, left footprints, left equipment, and came home. We've been to the moon, touched it, sampled it, analyzed it, and what we learned confirmed everything. The moon is Earth's sibling, born from the same material in a catastrophic collision 4.5 billion years ago. It's our partner, our stabilizer, our shield, and it's leaving. In the future, the moon will continue to recede, inevitably. In 100 million years, it will be about 400,000 kilometers away. Days will be about 24 hours and 7 minutes. A small change, barely noticeable, but cumulative. Tides will be about 10% weaker. The moon will appear about 4% smaller. Eclipses will be less frequent, because the moon's apparent size will be smaller. It won't always cover the sun. Some solar eclipses will be annular, not total. A ring of sun visible around the moon. That's already happening occasionally. When the moon is at apogee, farthest from Earth, in the future it will happen more often. Eventually, all solar eclipses will be annular. No more totality, no more corona visible, no more breathtaking moments of darkness at noon. The moon will be too small, too far, and we'll lose something. Aesthetically, scientifically, emotionally. In 500 million years, the day will be about 25 hours. The moon will be 430,000 kilometers away, 11% farther than today. Tides will be about 30% weaker. Coastal ecosystems will change. Species that depend on strong tides, intertidal organisms, they'll struggle, adapt, or go extinct. And the moon's stabilizing torque will weaken. Earth's obliquity will start to vary more, maybe 3 degrees instead of 2. Climate will be slightly less stable. Ice ages might be more severe, or less predictable. Life will adapt. It always does, but it will be harder, and the sun will be brighter, 5% brighter. Earth will be warmer, closer to the habitability edge. Oceans starting to evaporate. The equator might become too hot for complex life. Species will migrate toward the poles, toward cooler regions. But the habitable zone is shrinking. The moon's recession is a problem, but the sun's brightening is a bigger one. And they're both happening simultaneously, squeezing life from 2 directions. In 1 billion years, the sun will be 10% brighter. Earth's surface temperature will rise. The oceans will start to boil. Water vapor will thicken the atmosphere. Greenhouse effect will run away. Earth will become uninhabitable for complex life, maybe even for microbes. On the surface, life might retreat underground, deep in the crust, where water remains, where temperatures are stable. Extremophiles, thermophiles, clinging to existence. But the surface will be sterile, baked, dead. And the moon? It will be 450,000 kilometers away. 17% farther than today. Days will be about 26 hours. Tides will be half of today's. Weak, barely noticeable. and the moon's stabilizing influence will be significantly reduced. Earth's obliquity will vary by 5 to 10 degrees. Over millions of years. Climate chaos. But it won't matter, because there's no climate, not a habitable one. Earth is Venus. Hot, dry, lifeless. The moon watches, distant, helpless, as its partner dies. But let's not be too bleak, because there's another timescale, the tidal locking timescale. If Earth and the moon survive long enough, if the sun doesn't destroy them, then eventually Earth's rotation will slow enough that it becomes tidally locked to the moon. One face of Earth always toward the moon. Just like the moon is tidally locked to Earth, one face always toward us. This is the final equilibrium state, the end point of tidal evolution. How long does it take? Tens of billions of years, maybe 50 billion. The sun will be dead by then. Red giant, expanded, engulfed Mercury, Venus, maybe Earth. So it's academic. But theoretically, if Earth survives, it will lock. And when it does, the day will equal the month, the moon's orbital period, which at that point will be much longer, maybe 40 to 50 of our current days. So a day-night cycle lasting 50 days. Imagine 50 days of sunlight, baking one side, 50 days of darkness, freezing the other, extreme temperature gradients, violent winds, trying to equalize, heat from dayside to nightside. It would be brutal, uninhabitable, except maybe in the twilight zones, the regions between day and night, where the sun is perpetually on the horizon, dim, cool, stable. Maybe life could exist there, if it adapted, if it survived the transition. But it's unlikely, because the sun will have destroyed Earth long before. Still, it's the theoretical endpoint. Earth and moon, locked together, dancing, slowly, in a dead solar system. There's another factor. The sun's tidal influence. The sun also pulls on Earth, creates tides, solar tides. They're weaker than lunar tides, about half the amplitude, because the sun is farther away, much farther, even though it's more massive. The tidal force depends on mass divided by distance cubed. The moon is closer, so it dominates. But the sun's tides are not negligible, and they interfere with the Earth-Moon tidal locking. Even if Earth locks to the moon, the sun's tides will create drag, friction, energy dissipation, and that will destabilize the lock. Over geological time, the system is chaotic on very long timescales, billions of years. Predicting the exact outcome is difficult, but one thing is certain: the moon is receding, Earth is slowing, and the end state is uncertain, but likely catastrophic for habitability. Now let's talk about what the moon has done for us, not just in the distant past, but throughout Earth's history and into the present. First, the tides. We've talked about this, but it's worth emphasizing. Tides mix the oceans, vertically, horizontally. Nutrients from the deep are brought to the surface, where sunlight is, where photosynthesis happens. Phytoplankton thrive. The base of the marine food web, fish, whales, everything depends on that. And tides create intertidal zones, rich ecosystems, where land meets sea, tidal pools, marshes, mangroves, estuaries, some of the most productive ecosystems on Earth. Nurseries for fish, habitat for birds, carbon sinks. Mangroves sequester carbon, store it in sediments, mitigating climate change. All of this depends on tides, and tides depend on the moon. Without the moon, tides would be much weaker. Solar tides only, about 40% of current amplitude. The intertidal zone would shrink, ecosystems would collapse, fisheries would decline, human food security would suffer. The moon is not just scientific curiosity, it's economically important, ecologically critical. Second, stabilization of obliquity. We've discussed this, but let's emphasize the consequences. Stable tilt means stable seasons. Agriculture depends on that. Planting and harvest cycles, predictable rainfall, temperature ranges. If obliquity varied wildly, 0 to 85 degrees over millions of years, agriculture would be impossible. Civilizations couldn't develop. Hunter-gatherers might persist. But cities, nations, technology? No. You need stability, predictability, surplus food, stored resources, planning for the future. None of that works if climate is chaotic. If one century the equator is frozen and the next it's boiling. The moon gave us climate stability, and climate stability gave us civilization. It's that simple. Third, the moon slowed Earth's rotation to a comfortable speed, 24 hours. Imagine if the day was still 6 hours, like early Earth. 3 hours of daylight, 3 hours of darkness, rapid temperature swings, violent weather, constant storms. Adapting would be difficult, maybe impossible for complex life, certainly for humans. We need sleep, rest, darkness. If day-night cycles were 3 hours, we'd never adjust. We'd be sleep-deprived, cognitive function impaired. Society wouldn't function. But the moon slowed Earth, gradually, to 18 hours, then 21, then 24. A rhythm compatible with biology, with human circadian clocks. The moon gave us a day we can live with, literally. Fourth, the moon might have helped start life. This is speculative, but supported by research. Tidal pools, wet-dry cycles, concentrating organic molecules, facilitating polymerization, building RNA. Proteins, the building blocks of life. Without tides, without the moon, the chemistry might not have worked, or it would have taken longer, been less efficient. Maybe life would have started anyway, in hydrothermal vents, or elsewhere, but maybe not. Maybe the moon was essential. We can't know for sure, but it's plausible. And if true, if the moon helped start life, then every living thing, every bacterium, every tree, every animal, every human owes its existence to the moon. We are children of the moon, in a very real sense. Fifth, the moon gives us light at night. Moonlight, reflected sunlight, bright enough to see by, to navigate, to hunt. Our ancestors used moonlight for millennia, before artificial light. Full moon nights were special, safer, productive. You could travel, work, socialize. The lunar calendar, months, based on the moon's phases. New moon to full moon to new. 29.5 days. Cultures around the world, for thousands of years, used lunar calendars for agriculture, for religion, for festivals. The moon structured time, human time, and it inspired art, poetry, mythology, religion. The moon is in every culture's mythology, a god, a goddess, a symbol of change, of cycles, of mystery. The moon shaped human consciousness, our sense of time, of beauty, of the cosmos. It's not just a rock, it's a cultural artifact, a shared human heritage. And sixth, the moon inspired us to explore, to reach beyond Earth. The space age began with the moon, Sputnik, the space race, Apollo. We went to the moon because it was there, because it was close enough, achievable. Kennedy said we choose to go to the moon, not because it's easy, but because it's hard. And we did, in less than a decade, from decision to landing. 12 humans walked on the moon, brought back samples, data, inspiration. A generation of scientists, engineers, inspired by Apollo. The moon landings proved humanity could do great things, could achieve the impossible, if we worked together, if we committed resources, if we dreamed big. The moon gave us that, and the technologies developed for Apollo. Computers, materials, medicine, communication. They changed the world, spun off into countless applications. The moon gave us the space age, and the space age gave us GPS, satellites, weather forecasting, communication, Earth observation. Climate monitoring. All of it traces back to the moon, to the decision to go there. The moon is not just out there. It's in our technology, our infrastructure, our daily lives. So, what happens when the moon is gone? Or too far to help? What then? Well, humanity might not be around. The sun will render Earth uninhabitable in 1 billion years, long before the moon's recession becomes catastrophic. But let's imagine, hypothetically, that we solve that. We move Earth outward as the sun brightens, using massive engines or gravitational tugs. Science fiction, but theoretically possible. Or we terraform Mars, or build habitats in space. O'Neill cylinders, Stanford Torrey, space stations, artificial gravity, controlled environments. Or we leave, go to another star system, colonize exoplanets. Humanity spreads, survives, and billions of years from now, our descendants look back at Earth, at the moon, distant, separated, and they remember. The moon made us, gave us stability, gave us tides, gave us a 24-hour day, gave us seasons, gave us inspiration, and then it left. Slowly, inevitably. Physics. And we adapted. We survived. We thrived. Without it. Because we're clever. We're resilient. But we never forget. The moon was our first companion, our partner, for 4.5 billion years, and we owe it everything. Or maybe we don't survive. Maybe the sun's expansion destroys Earth and the moon, both consumed, vaporized, in the outer layers of the red giant sun. Billions of years from now, the moon's orbit will decay as the sun expands. Drag, friction, the moon spirals inward toward the sun and eventually crosses the Roche limit, the distance at which tidal forces overcomes self-gravity. The moon breaks apart, shatters, becomes a ring around Earth or around the sun. Debris scattered, and eventually the debris falls into the sun or is ejected out of the solar system by gravitational interactions, and the moon is gone, truly gone, no trace. Except in the geological record. On Earth, if Earth survives, tidal rhythmites, fossil corals, stromatolites, showing ancient day lengths, ancient tides, evidence of the moon that once was, and future geologists, if they exist, alien visitors or post-human AIs. They'll study those rocks and reconstruct the moon, its orbit, its influence, its story, and they'll realize Earth once had a companion, a giant moon, that stabilized it, protected it, made it habitable for billions of years, and then it left, or was destroyed, and Earth carried on, or didn't. The story ends, one way or another, but we're not there yet. We're here, now. In the Golden Age, the moon is visible, beautiful, close enough to stabilize, far enough to allow life. The day is 24 hours, the tides are manageable, the seasons are predictable. This is the moment, the brief window, in deep time, when Earth is perfect, for us, for life, for complexity. Before, 4 billion years ago, Earth was hell, molten, bombarded, uninhabitable. After, 1 billion years from now, Earth will be hell again, boiling, sterile, uninhabitable. But now, right now, it's perfect, and the moon is part of that, a critical part. We live in the Goldilocks moment, and we should appreciate it while it lasts. So next time you see the moon, look up Tonight or tomorrow, whenever it's visible, look at it. Really look. See the Maria, the dark patches, basalt, volcanic plains from billions of years ago. See the highlands, the bright regions, northosite, ancient crust from the moon's formation. See the craters, impact scars from meteorites, from the solar system's violent youth. And think, that object, that beautiful, distant object, is your sibling, born from the same catastrophe that created Earth. It's been with you, with us, with life, for 4.5 billion years. It stabilized Earth, kept the climate predictable, made seasons regular, made the day 24 hours, made tides, made intertidal zones, made life possible, made us possible. Every breath you take, every step you walk, every thought you think, you owe to the moon, and it's leaving. 3.8 centimeters per year, slowly, imperceptibly, but relentlessly. You're watching. Right now, a cosmic divorce, in slow motion, Earth and moon, once one body, now separating, forever. The moon is temporary, not eternal. It will leave or be destroyed in the far future, and Earth will be alone, wobbling, unstable, chaotic, unless we do something, unless we intervene. Build artificial stabilizers, or leave Earth, find another world, with its own moon, its own stability, or engineer new worlds, terraform, create habitable planets, from scratch. We have the knowledge. Potentially, the technology is coming, but we have to survive long enough to use it, and that requires recognizing, appreciating what we have now. The moon isn't just a pretty light in the sky. It's our life support system, our anchor, our shield, and we're losing it, slowly, but inevitably. Physics doesn't care about us, about life, about beauty. It just is. And the moon is escaping, and there's nothing we can do except appreciate it, study it, understand it, and prepare for a future without it. 4 billion years ago, a fish could almost touch the moon. It hung overhead, monstrous, dominating, driving tides hundreds of meters high, spinning Earth every 6 hours, hell planet, but stabilizing. 2 billion years ago, days were 18 hours, the moon still huge, but farther, calmer, life thriving, evolving, adapting to the lunar rhythm. Today, days are 24 hours. The moon appears small, gentle, but still essential, still stabilizing, still protecting. Tomorrow, the moon will be farther, days longer, tides weaker, until eventually, it's just a speck in the distance, and Earth wobbles, alone, chaotic, dying. We live in the golden age, the brief moment when everything is just right. Appreciate the moon. Thank the moon. Because without it, you wouldn't exist. None of us would. We are children of the giant impact, children of Theia, children of the moon. And the moon, slowly, silently, is saying goodbye. Look up tonight and say goodbye back, because in the deep time ahead, it will be gone, and all we'll have are memories, fossils, and gratitude for the 4.5 billion years it gave us everything.